Hello everyone. In today's video we are going to discuss about electric potential due to an uniformly charged thin spherical shell. So as you can see here, we have drawn a thin spherical shell and the radius of the shell is capital R. It's denoted by capital R. Now suppose you want to find out the potential at different points. Suppose first we want to find out the electric potential at any point outside the shell. Then we will find out the electric potential on the shell, and then we will find out the potential inside the shell. So for this, let us write the first case. When the point P lies outside the shell. So when the point P lies outside the shell, so let us consider a point P here and let it be at a distance R from the center of the shell. Let it be written as O. So in this case, so when point P lies outside the shell, in this case what we can write? We know that in this case E is given by 1 by 4 pi epsilon naught Q by R square. We have already deduce this expression from Gauss's theorem. So for the points which lie outside the shell, electric field is given in this manner. So now V can be written as electric potential. Now electric potential can be written as V integration of E dr, infinity to R. So we are acquainted with this equation. So suppose you want to bring the charge from infinity, unit charge, you want to bring a unit charge from infinity to a distance R. From infinity to a distance R. So we can write in this manner. So infinity to R, let us write this 1 by 4 pi epsilon naught as K by R square dr. So this can be again written as minus K and Q will come outside, infinity to R 1 by R square dr. So now this can be written as minus KQ minus 1 by R infinity to R. The result of the integration is 1 by R. So here we can write minus KQ minus 1 by R, minus of minus will give us plus. So it will be KQ into 1 by R. If we erase some, or let us write here, so therefore V is 1 by 4 pi epsilon naught Q by R. So this is same as the electric field due to a point charge. So for points outside, the potential is as if the charge is concentrated at the center. Okay, at a particular point, all the charge is concentrated. So now let us find out the electric potential when P lies on the surface of the shell. On the surface of the shell. So suppose your point P is somewhere here, and this is your R. So what we can write in this case? So in this case also, the potential can be written as 1 by 4 pi epsilon naught Q by R. So in this case, it is same as the previous expression, just we have written R as R, capital R. So R is equals to R here. Just we have replaced R with capital R, as R is equal to R since P is on the surface. That is, V is same, okay, everywhere on the surface. Now this was number B. Okay, this was number B. So now we are going to find out the case where the point PE lies inside the shell. Lies inside the shell. So in this case, we can say that electric field is 0 by Gauss's theorem. We have already found it out for the case of uniformly charged thin spherical shell. But we also know E equals to minus dV by dr. We know this. So let us put the value of 0 here. So again minus dV by dr. So here we can write from here V equals to constant. How can we write V equals to constant? Since you see minus derivative of V, okay, over R is 0. That means dV by dr equals to 0 means derivative of something which is constant is always 0. That means V is a constant here. Then only we can write this expression. If V is a constant, then only we can write this expression minus dV by dr equals to 0. Because we know differentiation of a constant term is always 0. Okay. So that means we can say that V is same at all points on the surface of this shell and also inside the surface. Okay, and that is also equal to, so it will be 1 by 4 pi epsilon naught Q by R. So it is same at all points on the surface and also inside the surface. Outside V will change, outside the shell V will change, but inside it is constant at all points. So now let us show the graphical representation of V with R. Okay. So this was our point, case number C. In case you haven't written C, so please write it as case number C. So now if you want to draw the variation of V with R. So let us draw a 2D coordinate system, and this is your uniformly charged thin spherical shell. V is in this side and R is in this side. So as you can see, in this case, if this is our 0 point, Okay, if this is our 0 point, so you can say that your V is same at all the points, and it is, suppose your V has a value of 1 by 4 pi epsilon naught q by r. Suppose somewhere here V has that value, and this is your surface where r equals to r here. So till this point your V is constant, that is it will have a fixed value. After that it will keep on decreasing. So here V has a value, k into q by r, and here in this part V will decrease in this manner. Okay. So as r will increase, V will keep on decreasing. So as you can see, as r is increasing, as the distance is increasing, V is decreasing. So this is our representation or variation of V with r, very important. So in the case where we solved in the case where we found out the electric field due to an uniformly charged thin spherical shell, there we had seen that if this is the shell, your electric field varies in this manner. If this is E, this is R. So your electric field is 0 at all points inside this surface. Suddenly it has some value on this surface, and then it decreases or we can represent it in this manner, that that R when increases, E decreases. Okay, in this manner it decreases, E. And compare this to, so here you can see it will have some value inside, and then it will decrease, and here it will have no value inside, that it will be 0 inside, and suddenly it will have some value. Okay, suddenly it will have some value. So E equals to kq by r square, or small r square you can write. So then it will decrease as 1 by r square. Okay. So these two comparisons are also very important. So that's all for today. Thank you.